I'm going to hand it over to our panelists. So I'd like to introduce Michelle Larson from the Adler Planetarium. She's the president and CEO, and she'll introduce our panelists. So thank you all for your attention, and we'll have a little bit more of a conversation.
All right, Shane did a great job at setting the stage there and teasing us just a little bit. And now we have 3 scientists who have worked on this project along with Shane, and they're going to help us understand a little bit more. So thanks for being here. I'll first introduce them, and then I'll take a seat and we'll moderate a conversation and for about 20 minutes, and then we'll have 20 minutes at the end for you all to ask questions as well. So first, down here on the end, we have, as you heard, the director of CIERA, Vicky Kalogera. Vicky is all of these faculty are faculty in the Department of Physics and Astronomy, so I wanted to say that up front so I don't have to repeat it every time. So Vicky is the Daniel I. Linzer Distinguished University Professor in the Department of Physics and Astronomy. She's the lead astrophysicist on the LIGO scientific collaboration that made the gravitational wave detection that you heard about. Vicky's an expert in black hole and neutron star formation in binary systems and in LIGO data analysis. She's been a member of the LIGO scientific collaboration for more than 15 years. Next to Vicky, we have Wen-fai Fong. And Wen-fai is a new faculty member at Northwestern. She joined us this fall in 2018. She's an assistant professor in the department. She spent the past few years planning for this electromagnetic follow-up, so that's very foresightful of you. And so was ready to go when this happened. She works to understand the mysteries of cosmic explosions and their environments through observations across the entire electromagnetic spectrum. And next to Wen-fai is Raffaella Margutti. And Raffaella is an assistant professor in the department. She's been working for more than a decade in the field of astronomical transients, including the most powerful stellar explosions in the universe and the disruption of stars by supermassive black holes, all events that emit these kind of strong signals. Her investigative tools consist of astronomical observatories, both on the ground and in space, and they also span the entire electromagnetic spectrum. So before you hear today, you have experts in gravitational wave astronomy and the entire electromagnetic spectrum of follow-up, and that's the conversation that we're going to have. Besides the people you see in front of you, the LIGO group here at Northwestern is much larger than that, including a number of graduate students and postdocs, and many of them are in the room today. So if you could just stand if you're a graduate student or postdoc on LIGO, it'd be great for people to see that you also contributed to these great discoveries. Thank you. It takes a village to do this kind of science, that's for sure. To get started, I thought we would play off of a few of the very evocative words that Shane said that I think you can give us some more insight into. In particular, when he said that the entire astronomical community was mobilized by these 100 seconds of gravitational wave observations that then led to the EM follow-up. So Vicky, I thought we'd start with you talking about what those early moments were like when it was the gravitational wave discovery and when it was all starting to come together. Tell us about that day.
So I was actually in Utah. I was on a family vacation. I had a 1-week planned vacation. And in fact, I had promised my family that I would stay offline completely. And had I kept my promise, I wouldn't know the signal had arrived, but of course I don't keep my promises. So especially when it comes to staying offline. So I woke up in Utah and the signal arrived around 7 a.m. Eastern time. So in fact, what I had planned for my day that day was that my husband, we were in Moab, Utah. It was the desert. We had come from the mountains in Colorado. And the kids were going to go with my husband to a hike in the desert. And I said, I'm not hiking in the desert. I'm going to stay at the spa. And you, my dears, can go hiking at 100 degrees. And after they left the room, I thought I will check my email. And then I saw the news. Then I saw the news of the discovery. I told this story to Dennis Overby, the science writer at New York Times. And then he wrote, Vicky Kalogera was hiking in Utah.
And your family
and my husband saw it and said, really? anyhow, long story short. So I saw the emails, and of course I canceled everything. And from that moment up until our announcement, basically I worked for the long 2 months.
What did it take to get ready for letting the electromagnetic astronomers know that they should mobilize?
So
how does that happen?
So what it takes is for us to analyze the data and figure out roughly where on the sky is the source. So localization, Shane said the word, localization is the first thing. So we have to analyze the data, and the first thing we knew immediately, 100 seconds is a long gravitational signal. The black holes were all 0.2 seconds, half a second, 2 seconds. So long signal, we knew it was neutron stars. Neutron stars means light is going to come out of this collision. So we knew it was really critical. We tell our electromagnetic partners. So we had to localize quickly. And we localized first, big arc on the sky. We let everybody know through electronic means, basically a telegram system we have within the astronomy community. And then we had a few hours to work on our data, the gravitational wave data, more and more, and improve the localization on the sky. And they can tell the story from their side. But what we knew already in those early morning hours is that the source was in the southern part of the sky. And it was morning here, but also still morning in Chile, in the southern part of the Earth, and the sky where you could see the source. But you couldn't see the source because it was the day. So yes, the event was there, and if it was the night, we could point the telescopes. But we couldn't. So we had a few hours to wait, and that allowed us to make the localization better. And it allowed them to prepare a little bit better.
Great, so lots of time spent trying to pinpoint exactly where, when they were ready, when nighttime came. And a critical piece of that story is that gravitational waves do not care if it's day or night. Gravitational waves go right through the Earth, right through everything, and so you will see them anywhere. Go ahead.
So we get to work 24 hours.
No, again, let's not go that way. Okay, great, thank you for that. So once LIGO was able to pinpoint, then Raffaella, why don't you tell us what then happened in your world of the EM follow-up, and then we'll get to Wen-fai.
Yeah, so it was morning, we got the alert about this new trigger in the sky, and we thought, it's gonna be one of these poorly localized LIGO events, so maybe let's wait a little bit. and then they sent us a better localization, and then we started planning because their localizations, they're good, but on astronomical terms, they're huge. They tell you something happened here. And
Somewhere out there.
So we have to tile the fields with our telescope. So we really had to get ready. And I kept telling Vicky, give me the best localization that you have.
We were texting.
Work hard.
So waiting and tiling while she's trying to give you a better localization, but you're working in parallel, basically, at that. Wen-fai, similar?
Yeah, and I think one of the key points of their localization was that it was basically right next to the setting sun. So not only was, gravitational waves don't care if it's day or night, and so it could be that the localization is up when the sun is up, but luckily the sun just set, and then we had our telescopes ready in Chile. So Raffaella and I are part of a program that used a telescope in Chile to actually observe this. So luckily the sun just set, and just as the sky was getting a little bit dark, we started taking images right away. So it was a really exciting endeavor, but consequently we only had maybe an hour of time right after the sunset to take images. So it was a really, truly exciting but frantic.
Because then the source set as well.
Right,
Yes.
exactly.
Yeah. So there was a brief amount of time to get information from the source.
If I can add one thing, I remember texting Raffaella. So I was working inside the collaboration, but I knew Raffaella was on one of the key teams that had one access to one of the telescopes that could tile the full region that we were providing to them. And I remember asking Raffaella, what's your cutoff time? How late can we give you information that is still useful for your team to plan ahead and then have the best information to find if there is a source, electromagnetic source. So she gave me a cutoff time, and then I went to the LIGO collaboration and I said, you know, this is our cutoff time. Now we have to work as fast as we can and provide the best localization by that cutoff time.
Way to drive things. There you go. I think a question that's burning in my mind, so if you'll let me take this prerogative, is we know you were planning to be at the spa that day and that got co-opted. We know LIGO is on all the time when it's running looking for gravitational waves, but we also understand that telescopes are heavily scheduled and there's a lot to look at in the sky, and so telescopes are scheduled all the time. So I have to ask the question is, what were these telescopes planning to do that night, and how did you drop everything and get to do this? Was there some protocol for that?
Yeah, so our programs are rated high enough that we can override.
This woman has a lot of power.
Yeah.
That's it.
Yeah,
You have override power,
we're not
too.
beneath offering bribes or. But yeah, we have these special types of programs where we can say, oh, we know that a neutron star merger is going to happen, or we hope it's going to happen. So when that moment happens, it's a very time-sensitive endeavor. So we basically take over the telescopes, but not without the permission of the people running those telescopes.
Yeah, you have to have some social skills. So.
Yeah, you do.
I was going to ask if you sent brownies or flowers to those that were supposed to be observing that night to make up for it. So,
Yeah.
yeah.
And I think one of the biggest things is just making those observers feel included, and they were super excited and to be part of this discovery as well. So we had a remote takeover of the telescope in Chile.
A remote takeover, so you weren't there at the telescope.
Right, yeah. Yeah, we didn't have enough time to fly down to Chile.
Yeah. So you just were here in Evanston?
Mm-hmm. Yeah.
So that's another, all of these telescopes are operated from afar. They can be operated remotely, and it allows for this kind of takeover when something happens.
Right,
Yeah.
right.
Yeah.
I was actually in Montana also getting ready for a vacation where it was actually right before the eclipse. So this happened August 17th. The eclipse was August 21st, I think.
Yep.
Yeah.
And so actually the entire astronomical and gravitational wave community were preparing their eclipse trips, and a lot of vacations were canceled. So, over this event. So, but personally for me, I had no lodging plan except a tent in the middle of Montana. So, so I prayed that I wouldn't get eaten by bears for 3 days, and I came back and was able to get back and ready to work.
That's a great story. All right, way to avoid the bears.
Yeah.
I want to talk a little bit about, now that we have had this event that has mobilized the entire astronomical community, now that includes gravitational waves and the full electromagnetic spectrum, what more have we learned? What more do we now know about two neutron star mergers than we knew before? And help piece that together for us. So let's go this way. Raffaella, you want to start there?
Okay. So one of the things that we learned is how the universe forms the heavy elements. So anything that is heavier than iron. So we usually say gold because people seem to care more about gold. Yeah. So heavy elements in our universe, now we know that they are formed during these mergers of stars. And that is actually very relevant for our own existence as well. So this is one thing.
We're in a chemistry classroom, so we might as well point that out. We all remember from chemistry, it takes a lot of energy to push heavy elements together, and so regular burning stars don't have enough energy in their normal cycle to get things past iron pushed together. It takes more energy to put them together than you get out of it. But this type of a cataclysmic event puts enough energy into the system to now start slamming things together past iron. So that's how we get these heavy elements.
Anything past iron over there, so number 27 more, all of those are coming from neutron star mergers. That is what we know right now. So I think it's extremely
So the whole bottom of that chart, we now know where it comes from. That's fantastic.
That was a huge question mark that we had before.
Great, huge question mark. That's what science is about, and this is fun when we learn it. Wen-fai?
Yeah, I think this event had many firsts associated with it. It's really, one of the pinnacles, I think, in astronomy that will be written about in textbooks, high school textbooks and college textbooks for a really long time. I think that's really exciting. One of the things I think was most exciting about this event was that we found a gamma ray burst in association with a gravitational wave signal. So that slide that Shane showed where you see this kind of uptick, or what do you call it, chirp signal in gravitational waves, and then followed by this intense flash of gamma rays. So gamma rays are the most energetic form of light that we're able to detect. And these gamma ray bursts have actually been detected for a really long time, dating back to the 1960s. And this special class of very short flashes, these short duration gamma ray bursts that we saw in conjunction with this gravitational wave signal, we actually never had direct evidence of what their origin was in the universe, but we saw them once a month or so, for the past 20 or so years from gamma ray satellites. So I think now that we see something LIGO telling us there's a neutron star merger, and then followed by gamma ray bursts, it really solves this 40-year-old puzzle of what these intense flashes of gamma rays are from.
That's fantastic. I think it was Rutherford that said that astronomy is like stamp collecting, because there's a lot of observing and classifying. And so for decades, we've been seeing gamma ray bursts and making catalogs of them and picture books of them and family albums of them, and putting them together with light characteristics. We've been doing this for decades, and for many had no idea what caused them, right? But we knew it was important to keep observing them and to keep classifying them, and that eventually we would observe enough to understand what they were. And as you're saying, this is the key that finally identified that these short ones were two neutron stars together. So we can check off that stamp collecting album and say we know where these came from. That's great. Vicky?
So I want to comment from the gravitational wave side alone. It's the first time we actually observed directly the merger of two neutron stars. So this kind of phenomenon had never seen before, knowing that it is two neutron stars coming together. So that's a first. And it's a first because of course, we had seen the gamma ray burst, and even we had seen signatures or hints of the formation of the heavy elements. We couldn't prove fully this is what we were seeing, but we had the hints. Now, for the first time, we have, through gravitational waves, the proof that it is, in fact, two neutron stars. And the reason we have the proof is that only through gravitational waves you can measure the masses. Okay? So the mass measurement comes from the gravitational waves. The phenomenal thing that I'll make a personal remark in the following sense. I am a theoretical astrophysicist and not an observational astrophysicist as Raffaella and Wen-fai are originally. And in that sense, I grew up making predictions for what the data will reveal one day. And people in a different field than mine made predictions about neutron star mergers colliding and forming a gamma ray burst, and made predictions about neutron stars colliding and forming heavy elements. And these observations, these electromagnetic observations, are now the proof. So it's in a way a triumph of observational experimental astronomy coming together with theoretical predictions over many decades and providing the proof of a lot of predictions. And I think that is quite stunning. Often we find excitement into disproving theories. Well, this one event so far has proven a lot of theoretical predictions. And I find this quite satisfying, given that my upbringing in science comes from theoretical astrophysics.
And in that sense, it sets a new future, because
Yes.
from now going forward, we will have both eyes on the universe, all of the light that we can collect, as well as now adding the gravitational waves. So it starts a new era.
That gives us more information and new information.
Yeah, great. One last question, and then we'll turn the time over to the audience to ask some questions. I'd like to talk about this upheaval that has happened in gravitational wave physics first, when the first gravitational wave announcement was made in February of 2016. There was a drop everything upheaval for 6 months while the LIGO collaboration was working hard to eat at their desks and skip their vacations and verify the data and make the first announcement. And just when those email numbers were getting down under the thousands and life was getting back to normal, then this EM detection happened, and now you two got to join in on the drop everything and don't get eaten by a bear and make sure that you have Wi-Fi signal. That's likely not sustainable, that we can do this to ourselves as scientists all the time. So give me, each of you, some thoughts on where this may evolve. What does this look like as these become not mundane, but what does the steady state look like for multi-messenger astronomy? How are we going to deal with these kinds of things? And Wen-fai, why don't you start this one?
Yeah, I think this really is a nascent field of observation, at least on the electromagnetic side. We've, as Vicky noted, we've been making predictions, or the community has been making predictions for the past several decades. And now we're starting to have these observations. And yes, it's definitely, having lived through the past 2 or 3 months, it's definitely not sustainable to do it all at once. I think really what struck me the most was kind of the teamwork involved across the entire astronomical community. So we had people from kind of all different backgrounds, not necessarily in gamma ray burst science or neutron star merger science, but everyone studying explosions or the galaxies, kind of gathering together to observe this event. And I think the steady state it's really a great way to attract larger groups and big students. So for me, I actually just moved to Evanston 4 days before this event happened to start this new job. And so it's really an exciting time to be able to tell students, not just we're planning for this era, but this era is here, and now you can come work and observe. So I think really teamwork is how I view the steady state.
More help.
More help.
More help.
Yes.
Great.
Yes.
Vicky?
So if this were the first gravitational wave discovery, I would probably not have an answer for you. Because when the first time we discovered the 2 binary black holes, and we lived through those crazy few months where we lived through something unsustainable, I didn't know how are we going to do this? How are we going to keep doing this? But then somehow we did it. I'm looking at Shane. We now have announced 6 binary black holes, and by the time the 6th came, which, by the way, the 5th we announced, but the 6th event, it's a bit of, the order is a bit complicated. But by the time, let's say, the 6th came, it was 3 days before the 2 neutron star signal came. In the 1 week I was taking a vacation. 3 days before. And it was like, yeah, we got a binary black hole signal. Yeah, I have some work to do. It's OK. But we can go out to dinner. So by the time it was the 6th binary black hole, we could do it. It was sustainable. It had become sustainable. But if you ask me that question 1 month or 2 months after the first announcement, I would look at you in panic and say, I don't know how we're going to do it.
Okay. It didn't feel like it at the time.
It didn't feel like it was going to be sustainable.
So more help,
somehow we're
perspective, right?
Perspective.
So more help, perspective.
Exactly.
What do you want to add to that storyline?
I like to remark that this event is not over. It's still going strong.
Very good point. It just came out from behind the sun.
Yes, it's going to come out on December 1st. And so actually, I look at my next 20 days, and maybe I'll answer to you after.
You don't have perspective yet. You're still in the first one. That's a good answer. That's a good answer. So our hope is that soon the electromagnetic partnership to the gravitational wave 2 becomes sustainable and mundane. But right now, you're still in your first one.
Yes,
That's a very good point.
Yes.
That was good. Excellent. Well, thank you all for that conversation.